Hello everyone, this is Dr. K. Amudha, Associate Professor, Department of Science and Humanities Physics, R&D Engineering College. In this video, I am going to talk about fiber optic sensors. Introduction. Laser light was invented in the year 1960. After the invention of laser, there is a many advancement in the application of optical fiber communication systems. In this optical fiber communication systems, informations like um, data, voice, telemetry, video are being transmitted over a longer distance or computer networks or LANs. And in this technology, light waves are used to transmit the data over the fiber by changing the electronic signals into light. Some of the excellent features of this technology includes it is very less weight and low attenuation, and then it is used for longer distance signal transmissions, and the signal is secured and so on. Significantly, the telecommunication technology has changed the recent advances in the fiber optic technology. Last revolution appeared as designers to combine the protective results of optoelectronic devices with the fiber optic communication devices to create fiber optic sensors. Many of the components associated with these devices are often developed for the fiber optic sensors application. The ability of the fiber optic sensor has increased in the place of traditional sensors. In the picture, you could see the fiber optic sensors which is being displayed. Now, we move on to the types of fiber optic sensor systems. These sensors can be classified based on the following category. First is, based on the sensor location, the fiber optic sensors are classified into two types. They are intrinsic fiber optic sensor, extrinsic fiber optic sensors. The second category is based on the operating principles. It has been classified into three types. They are intensity based, phase based, and polarization based. Third category is based on application. Fiber optic sensors are classified into three types such as chemical sensor, physical sensor, and biomedical sensor. Now here in this picture, some of the optical sensors are being shown. Displacement sensor will look like this, and then you have the pressure sensor and the temperature sensor. From this picture, you will understand it is very small and compact in size. Now, what is fiber optic sensor? It is basically a transducer. It is used to convert one form of energy into another. That is, they are also called as optical fiber sensors. Use optical fiber or sensing element. So mainly in this sensor, optical fiber is being used. Okay. So these sensors are used to sense some quantities like temperature variations can be measured in the area, pressure, vibrations, displacement of the object, rotations or concentration of chemical species, etc. Fibers have so many uses in the field of remote sensing because they require no electrical power at the remote location and they have a tiny size. Next, fiber optic sensors are supreme for insensitive conditions, including noise, high vibrations, extreme heat, wet, and unstable environments. These sensors can be easily fit in small areas and can be positioned correctly wherever flexible fibers are needed because the optical fibers are very flexible in nature. They are thin and compact. The wavelength shift can be calculated using a device, optical frequency domain reflectometry. The time delay of the fiber optic sensors can be decided using a device such as an optical time domain reflectometer. Now in this picture, we will see the block diagram of a fiber optic sensor. So in the block diagram, you could see that optical source is a main component. So you have a source here, which is a light emitting diode, laser diode can be used. Next, definitely you should have an optical fiber sensing element. Okay, you could see the optical fiber and sensing element. Optical detector is there, and N processing devices, which may be optical spectrum analyzer, oscilloscope, etc. So you have a source, then you have this measuring environment, then from the measuring environment is mostly we use this optical fiber, which is a transducer, which is used to convert one form of energy into another. Then from that it is being connected to a detector, which detects. Then from the detector it is being sent to a electronic processing unit. These sensors are classified into three categories based on the operating principle, sensor location, and the applications. That is being already being explained to you in the previous slide. Now, intrinsic type fiber optic sensor. In this type of sensors, sensing takes place within the fiber itself. So, intrinsic sensor is otherwise known as active sensor. The sensor depend upon the properties of the optical fiber itself to convert an environmental actions into a modulation of the light passing through it. How here, one of the physical properties of light signal may be used in the form of frequency, phase, polarization, intensity. The most useful feature of this intrinsic fiber sensor is it provides distributed sensing over long range distances. The basic component of this intrinsic fiber optic sensor is shown in the figure. So you should have definitely a light source, then the optical fiber which is used as a transducer and which is placed in the measuring environment, and the light detector. If the measuring parameter directly acts on the fiber, then produces a change in the amount of optical signal passing through it. Then the sensor is known as an intrinsic sensor or an active sensor. Examples are temperature sensor, pressure sensor, liquid level sensor, intensity sensor, phase sensor, etc. Next is the extrinsic type fiber optic sensor. In extrinsic type fiber optic sensor, the fiber may be used as an information carrier that shows the way to a black box. It generates a light signal depending upon the information arrived at the black box. The black box may be made of mirrors, gas, or any other mechanisms that generates an optical signal. These sensors are used to measure the rotation, vibration velocity, displacement, twisting, torque, and acceleration. The major benefit of this sensor is their ability to reach the places which are otherwise unreachable. If the measuring parameter does not directly act on the fiber, but it just transmits the optical signal and the fiber acts as a guiding medium, then the sensor is known as extrinsic sensor or passive sensor. So in this extrinsic or passive sensor, the fiber is used only to transmit and receive the optical signal. It is not used to sense any parameters. So if you look into the diagram here, so definitely you should have a light source at one end from which the light is sent to this modulator. Modulator is where you make use of this input fiber which is used to transmit the light. Then from the light modulator, that is the environmental signal, the signal is received through this output fiber. Then it is fed to a light detector. Some of the examples of this is displacement sensor, laser Doppler velocity sensor, liquid level sensor, etc. First, we'll see about the displacement fiber optic sensor, which is an extrinsic type sensor. We'll see about the principle, description, and work. Displacement sensor, which is an extrinsic sensor, and the principle is Light is sent through a transmitting fiber and it is made to fall onto a moving target. Then the light reflected from the target is sensed by the detector. With respect to the intensity of light reflected from its displacement of the target is measured. Now description. It consists of a bundle of transmitting fibers coupled to the laser source and a bundle of receiving fiber coupled to the detector as shown in the picture. So this is a picture of the displacement sensor. So you have a laser source and a bundle of transmitting fiber, and the light is received from the laser source. Then it is incident on the moving target. Then from the moving target, the light is received, okay, and then it is received by the receiving fiber. Then it is sent to a detector. So the axis of the transmitting fiber and the receiving fiber with respect to the moving target can be adjusted to increase the sensitivity of the sensors. So the axis of the two fibers with the target can be increased to increase the sensitivity of the sensor. Now let us see about the working. Light from the light source is transmitted through the transmitting fiber and it is made to fall onto the moving target. Then the light reflected from the moving target is made to pass through the receiving fiber and the same is detected by the detector. So the light from the source is transmitted to the fiber, then it is incident on the moving target, then the light reflected from the moving target is received by the received fiber and then it is detected by the detector. Based on the intensity of the light received, the displacement of the target can be measured. That is, if the received intensity is more than we can say, then the target is moving towards the sensor. If the intensity is less, then we can say that the target is moving away from the sensor. Suppose the target is moving towards the sensor, then the intensity of light received by the receiver will be more. The same can be detected by the detector. On the other hand, if the moving target is moving away from the fiber, then the intensity received by the receiving fiber will be less. So in this way, the displacement of the target can be measured. Now we move on to the next type of sensor, which is a temperature sensor, which is also called as the active sensor. Now, what are all the components of this temperature sensor, which is also called as a pressure sensor? They are laser source, beam splitter, reference fiber, test fiber, lens system, and the interference pattern. So you have a recording medium where you can get the interference pattern. What is the principle of this temperature sensor? It is based on the principle of interference between the beams emerging out from the reference fiber and the fiber kept in the measuring environment. Okay, so which means here two fibers are used. One is called as a reference fiber, another is called as a test fiber. The reference fiber, which is isolated from the measuring environment, whereas the test fiber is kept in the measuring environment to be sensed as shown in the figure. Separate lens systems are provided to split and collect the beam. Now we look into the diagram. So this is what is a diagram. So if you see here, you have the laser source, beam splitter, and then lens arrangement. Okay, and you have the two fibers here, reference fiber, and then the test fiber. The test fiber is of optical fiber which is kept in the measuring environment. Then the light from the two fibers are made to superimpose and it is being recorded in the interference recording medium and then you get it in the form of interference pattern. So now if you see, it consists of a laser beam to emit light. A beam splitter is made up of a glass plate which is inclined at an angle of 45 degree with respect to the direction of the laser beam. Now working, when you see, a monochromatic source of light is switched on, okay, and the light emitted from the laser source. So laser source is switched on and the light is made to be incident on the beam splitter. The beam splitter is kept at an angle of 45 degree inclination, divides the beam from the laser source into two. So main beam and the splitter beam. Okay, the main beam, it is being entering exactly at right angle. Both the beams are right exactly at the right angles to each other. So the main beam, which is made to focus onto the lens arrangement L1, and then it is focused onto the reference fiber, okay, which is isolated from the environment to be sensed. Okay, so the main beam passes through the lens L1 and it is focused onto the, so it is being focused onto the reference fiber, which is isolated from the environment to be sensed. So it is isolated from this. So this is the testing environment. So it is totally being isolated. Next, the beam after passing through the reference fiber then falls onto the lens L2. So after passing onto this reference fiber and it propagates by means of total internal reflections, and then it is then passing on to the falls on to the lens L2. Okay. Next, the beam, splitter beam passing through this L3 and it is focused onto the test fiber kept in that environment to be sensed. So the test fiber is kept in the testing environment. So the beam, after passing through this lens L3, it is made to pass through this test fiber, undergoes total internal reflection, which is kept in the measuring environment. Okay. So in the measuring environment, we may be noting the temperature changes, pressure changes, etc. Now the splitted beam after passing through the test fiber is made to fall onto the lens L2. So after passing through this test fiber, it is again made to fall onto L2 as that of this reference fiber. Okay. So these two beams after passing through the fibers produces a path difference due to the changes in parameters such as pressure, temperature, etc. So the two beams, one directly coming from the reference fiber, another which is coming from the testing environment, will have a path difference. So they two superimpose. So definitely you have a phase difference will be there. So they two superimpose on each other and interference patterns will be recorded in the recording medium. Therefore, a path difference is produced between the two beams causing the interference pattern as shown in the figure. Thus, the change in pressure and the temperature can be accurately measured with the help of interference pattern obtained. So, by analyzing the interference pattern, it is able to measure the temperature and the pressure which is prevailing in this testing environment. So this is what is the actual picture of this intrinsic sensor. So it is also called as intrinsic sensor, active sensor. So phase and polarization modulation is being recorded here. So it is also called as phase and polarization fiber sensor. So when you see the applications of fiber optic sensor, it is used in the wide range of applications such as measurement of physical properties such as temperature, displacement, velocity, strain in the structures of any size and any shape can be measured. In real time, monitoring the physical structure of health. Buildings and bridges, tunnels, dams, heritage structures can be monitored. Night vision camera, electronic security systems, partial discharge detection, and measuring loads of vehicles. These are the important applications of fiber optic sensor. Thanks for watching.